be with you, but I hope that this is going to work well. The lecture is about the Virgo detector. It's not exactly going to be as I announced in the abstract because there was not the time for me to prepare some of the slides as I wanted to. But anyway, I think I have something interesting for you anyway. This here is a picture, as you can see, of an arm of the Virgo detector, and it's a really beautiful site. And I hope you will have a chance to visit the Virgo detector at some point. It's really worth a visit. Let me see. Okay, since we haven't really met, let me just briefly say where I'm from and what we are doing here. So I'm from the Gran Sasso Science Institute, and this is a new institution in L'Aquila. It was created, so some of you or all of you might remember that there was a big earthquake in L'Aquila in 2009, which destroyed the city almost completely. At least the central part was mostly completely destroyed, with many fatalities as well. And now there is nearby L'Aquila, there's an underground laboratory which is really world famous, which was completely left intact by the earthquake. The National Laboratories of Gran Sasso, and the experiments somehow had to go on because these are important experiments, and so as an initial tool also to get people back into the underground laboratories, but also to be part of a strategy to rebuild the city. L'Aquila, the Gran Sasso Science Institute, was created. And it was operated by, or supported by INFN, the National Institute for Nuclear Physics, for many years until it became a public university some years ago. And that's where I am inside this building. And we have a group of about 20 people in gravitational wave science broadly, be it theory, data analysis, or multi-messenger science, instrument science. What was lacking so far here was experimental activity. We are doing all our experimental work at the moment with Virgo, but in the future that is going to change because we have also now finally laboratory space and things like that coming, and so that completes essentially our group. And yeah, we have a lot of fun. Okay, that's about me. So I'm here and full professor here, together with Marika Branchesi and Eugenio Coccio, who's not on this picture. Okay, so let me then summarize the program for today. So instead of giving you a broader overview then of the Virgo detector with a couple of technologies that are relevant for the upcoming science run, I in the end decided that I will focus on one of these technologies. And accordingly, I will then present to you, first of all, about the seismic environment at the Virgo detector, the gravitational coupling between seismic fields and test masses, and the mitigation of the noise that is produced in that way. So all of that is under the framework of Newtonian noise cancellation, which is one of the new technologies that is being implemented at the Virgo detector right now, to prepare it for the next science run. Okay, so the Virgo detector is in or very nearby Cascina. Cascina is a smaller city in the nearby Pisa, and okay, Pisa is near the coast in Tuscany, and I mean it's interesting. First of all, that of course in Europe you are having a hard time to finding a site where there's no human activity nearby. So also here, of course, there are roads nearby and farmers working. So these are all considerations that one has to make when you have to choose a site, whether this is fine or not. But at that time it was deemed okay. And in fact, I think this site doesn't really have that much of a big or positive impact on detectors of the current generation. Now, the construction started a long time ago, in 1996. So that means the infrastructure that we have today is really old. It's 26 years old. So that means it's also showing signs of age. It the first observations were done really in 2017, or in some sense you might even say it wasn't much of observations, but of non-observations, which led to quite of a breakthrough together with the LIGO detectors. The first big example was not the first signal that was seen together with Virgo, but the first where they made a really big impact was the merger of the Newton star binary, where the non-observation of the signal actually was telling people where to look in the sky. And that enabled, together with the LIGO detectors, really the big multi-messenger campaign that followed. Alain Brier on the French side and Alberto Giazzotto were the main coordinators in the very early phase of the project. Okay. So then at the end of the last science run, this was the situation in terms of the sensitivities. And you see that, okay, the black curve here is of the GS600 detector, which is the British-German detector, which is a significantly smaller scale at that time because of historical reasons, because in the midst of the planning of the detector, there was the reunification in Germany, and that removed essentially all chance to get big money for this project. So it became a smaller scale project, and you see this also here in the sensitivity curve, of course. Then we have the two LIGO detectors, almost identical in sensitivity, almost. And here, the Virgo detector, at low frequencies, it can quite compete with the LIGO detectors. Also, you have to keep in mind the Virgo detector is a kilometer shorter. It's 3 kilometer arm length. So any displacement noise results in slightly higher strain noise compared to LIGO, simply because the arms are a little bit shorter. Now, okay, at low frequencies, that's fine. At high frequencies, there's a more substantial difference, or there was in 03, between LIGO and Virgo detectors. And this was connected to the optical configuration most of all. I will show this on the next slide. But anyway, so the performance of the Virgo detector was really quite good in the last science run. Now, in the upcoming science run, Virgo will have a new look. And this is part of a project which is called Advanced Virgo Plus Phase 1. So here is how Virgo is going to look like in the upcoming observation run. And there are three main configurational changes. The first is the implementation of this mirror here, which is, well, some people call it a signal recycling mirror. I prefer to call it a signal extraction mirror, because the job of this mirror here really is to extract the signals that are kind of trapped in these arm cavities. And that enlarges the observation band that you have. So you can see essentially here, if you compare the Virgo detector starts to lose sensitivity at a lower frequency here. And this earlier rise is connected to the fact that it didn't have at that time this kind of mirror here. The other thing, and you have heard from Lisa about this already, is the the quantum or squeezed light filter cavity, a filter that is optimizing the way we implement squeezed light sources in these detectors to optimally profit over all frequencies from squeezed light. And so these two changes have been made already at the site, and they are still part of commissioning, or subject to commissioning. So this is still work in progress to get to best performance. Now, and I should say, and I'm not going to talk about this, it is an interesting topic for Virgo. This year, there was a reason why that was not implemented at an earlier phase, because LIGO had this mirror already in the last science run, and Virgo didn't. And the reason for it was because this mirror is creating an, let's say, optical, or it's creating instabilities, if you want, or near instabilities. You're getting close to an unstable behavior of your optical system. And that makes now the whole interferometer really difficult to operate. And that is kind of reflected in certain challenges that the commissioning team currently has. And these were avoided on purpose But now they are, of course, facing these challenges, and we'll see where we get with that. And the third component is the Newtonian noise cancellation system. I will show this now in more detail, but just to anticipate what that really is you deploy on the side, at the Virgo side, you are deploying more than 100 sensors essentially. That's what we have at the moment. In the vicinity of the task masses, all around the task masses, you have deployed sensors. And you use the data of these sensors to, well, first it's a monitor of the environment of the seismic fields, and then you can pass all of these data through an optimal filter. And the one output of the filter, this is what you want to subtract from your gravitational wave data. So in some sense, in post-processing, you can clean up your data. And we'll see, I mean, there's a story to tell about this. Together with these main configurational changes, let's say, there are other changes that will happen, like increasing laser power, lowering the overall optical loss in the system, but that's mostly it. And this should bring us a little bit closer to the LIGO detectors at higher frequencies. Okay, fine. Now I go over to the Newtonian noise cancellation system. And if you want to understand that one well, you really have to understand the seismic environment of the Virgo detector. And I have to introduce a little bit about seismic spectra and all of that, and disturbances. So here is a seismic spectrum measured at the Virgo site. In reality, it's not just one spectrum. It's measuring over a long time, over the course of a year or a month in this case, actually. You are measuring many separate seismic spectra, and then you're putting them all into a histogram. And this is what you get. So you have a level of ground vibration as a function of frequency from 10 millihertz to 20 hertz. And the units of this is in ground velocity, so or speed, if you want, meters per second per square root of hertz. So essentially, what amount of vibration amplitude you have as a function of frequency. And so you can see, okay, let me go through this step by step. So first of all, in addition to the histogram, you have two lines here, these dashed lines, and these are called the new low noise model and the new high noise model. In reality, these are not so new anymore. These are from the 90s, but they were called by Peterson, a seismologist at that time, like that. And these are, especially this one, the lower one here, is an extremely useful reference, because that is telling you, if you measure a seismic spectrum anywhere on Earth, not in Italy, not in the US, like anywhere, you will find that the spectrum at no frequency will lie below this curve. Now, only in very rare exceptions known today, for example, boreholes in Antarctica or things like that, you can find sites where the spectrum will go a little bit below this curve, but it is otherwise really working quite well. So, for example, making a borehole at a very remote location like Sardinia, let's say, you will still measure a seismic spectrum which will be above this curve. And this is interesting. So this is giving you a good reference, because it means this is as quiet as it can get on Earth. So you can see the Virgo site is really far from that. We are talking about 2 to 3 orders magnitude, or maybe even more, excess noise compared to that level at the Virgo site. And what is all of that? So first of all, there are, let's say, 3 main bands here to show. The low frequency band up to a few tenths of millihertz, where the ground motion, and I'm actually not so sure that this is really measured ground motion, because knowing what type of seismometer was used, this might also be here at least instrument noise, some kind of readout noise. But generally, you will observe here seismic signals produced by wind or earthquakes. Now, then you have this blue band here, which is the oceanic band. So everything that you see here is dominated by what happens on the oceans. I will show this on the next slide, what really produces these signals here. But there are two main features, which we call primary peak and the secondary peak. And this is all connected to ocean wave phenomena. And you can see that at the Virgo side, you have like in reality 3 peaks, but these two are in reality 2 secondary peaks because they are produced by different parts of the ocean. Now, at high frequencies, let's say above a few hertz, you are observing at the Virgo side anthropogenic noise. And this can be from outside the Virgo detector, which, traffic, for example. But it is also produced inside by the Virgo infrastructure. So this is an important point that we will come to as well in a bit. Okay, so that is how it looks like. And now going over a few examples. So just to clarify about this, the oceanic disturbances. So the primary peak is produced in the following way. If you have an ocean wave or sea wave coming in and it enters the shallow waters, so you have to understand that under this ocean wave, if it's traveling, if it's just a single wave traveling towards the coast, let's say, then the pressure field that exists inside the water because of that sea wave is evanescent, which means it has an exponential amplitude decay. And so this pressure field couples very weakly to the sea floor simply because it is evanescent. But then if you enter the shallow waters, then the distance can be short enough so that this evanescent wave still shows some coupling to the ground floor, to the sea floor. And so at this point, pressure fluctuations in the water can now convert into seismic waves here at the sea floor and propagate away. And that's the primary peak, and it's a little bit weaker. Now the big peak in the spectrum, which you can really observe everywhere on Earth, there's no way to escape this kind of disturbance, is coming from standing ocean waves. So you have essentially 2 counter-propagating wave fields, and then they meet somewhere to form a standing wave. And then now it turns out that if you have a standing ocean wave, then it emits a pressure wave into the water. So this is not anymore an evanescent pressure field. It is now a propagating pressure wave, an acoustic wave, if you want. And that one can go really far to the deeper part of the ocean and then couple here to the sea floor. And these kind of situations where you have counter-propagating waves are very common because any kind of cyclone that happens, for example, in the northern part of the hemisphere, on the ocean will produce in some way counter-propagating wave fields, and then you have this as a typical feature of associated with storms, for example. Okay, this about the oceanic band. Now, before entering into other examples, let me first say a few words about seismic waves, just to make sure that we are on the same page. There are 2 types of seismic waves: the body waves and the surface waves. And the body waves are seismic waves that can propagate freely in all directions through Earth. And the surface waves are confined to a propagation along the surface. And there are 2 different types. I'm showing only one type of surface wave. This one here that is shown is the Rayleigh wave. And the Rayleigh wave is interesting because it has a circular or elliptic particle motion that it induces on each particle in the ground. And so it's a retrograde motion. And this is how it moves forward here. And it has elements of shear and elements of compression. So it's kind of a mixed type of wave. But it is, for earthquakes, it's known that this here is typically producing the largest damage. It is the largest amplitude disturbance that is produced by earthquakes in the end. Now, the body waves are the ones that propagate faster because they can take, first of all, shortcuts because they go 3D, and they have three-dimensional trajectories through Earth. But then they are also typically, since they are entering the Earth into deeper layers, they are also seeing a faster medium. And so they are not only taking geometric shortcuts, but they are also entering the fast parts of the ground. And so they are typically the ones, for example, that are fastest to reach you when produced by some seismic source. And here you have the compressional waves, which are longitudinal polarizations, if you want. So it's a longitudinally polarized wave, and so it is compressing and decompressing the ground. Then there are two other polarizations, which are the shear waves, the two transverse polarizations of a seismic wave. And there's no compression or decompression. It is just inducing this kind of shear motion here. Okay. So these are the three types of waves, and we have to understand these and be able to model these if we want to also understand how seismic fields couple with our test masses. Now, returning to examples for the seismic environment at the Virgo site. So here, for example, you can see the relevance of the external environment of the Virgo detector. So as I already mentioned, there are roads, highways nearby the detector. And interestingly, if you just have a highway and cars passing by, there's not really much of a disturbance being produced generally. But then there are specific points where this changes, and these are the bridges. And so it is simply the fact that if you have a highway bridge, for example, then there are little steps because it's a segmented kind of architecture, right? And so, for example, a heavy truck enters the bridge, and it has a specific point where it is making like tuck with the wheels over a small step, for example, in the bridge, how it connects to the rest of the road. And this is producing then measurable seismic disturbances. So here, the upper time series is measured directly at the highway bridge, and you can see it is really the passage of it's not really clear from this plot, but this is what the people wrote who analyzed this. These three moments here, where the big outliers were, this is where a truck was passing by, and then when you look at seismic measurements at the same time at the central building of Virgo, you see that at the same time there were also disturbances visible at the Virgo site. So you see that this kind of environment really it matters. Now, also what happens inside the Virgo buildings is important, and one of the big drivers of, well, first of all, acoustic noise, but then also seismic vibrations is the ventilation system. And people have looked at this quite carefully also at LIGO, but also at Virgo to see how much of an excess noise we really get from it. And here for the acoustic field at Virgo especially, it's not that bad at LIGO, but at Virgo especially, the acoustic excess noise is immense produced by the ventilation. So this they found out with a ventilation switch-off test. And you see that when the ventilation is on, it is at Pascal per root hertz. So this is a measure of the air pressure fluctuations, so sound, if you want. And when you switch off, then you are reducing by more than an order of magnitude at some frequencies the acoustic noise. And there are also effects on the seismic spectrum, which is a little bit less, and not so much connected to the airflow, but to other things connected to the ventilation, which is really the air conditioning, which relies on water pumps and chillers and whatnot. And so these produce vibrations that you can see with seismometers. And if you switch these elements off, then you essentially observe that decrease in the seismic disturbance. So that's interesting. Now for Virgo, what happened is when they started to investigate this very carefully and to make comparisons with LIGO, while LIGO doesn't see that much excess noise from ventilation, some things were learned about what was different between the two sides. And so they could then make modifications to the infrastructure, the EGO team. And that was really already helpful because it led after these measurements to some reduction, at least, of the acoustic noise. But still, these are lessons learned which are not only important for Virgo, but it is also tremendously important for us to understand these things when we plan the next generation detectors. And Matt is going to talk about Cosmic Explorer. I'm specifically about this. I will tell you a bit more tomorrow when talking about the Einstein telescope. Fine. Now, another example, the last example, is the wind turbines, and they are, about 6 kilometers to the Virgo buildings. There are wind turbines, and they also produce strong noise. Now more narrow band, but at several frequencies. And people looked at this carefully by deploying essentially seismometers at the turbines, but all the way along a road to the Virgo side. And to see how that disturbance behaves as a function of distance to the turbine, and then you can see essentially the results of these studies here, the main results. So you have at several frequencies, you see like big disturbances when you measure directly at the turbine, but then it is quickly attenuating in amplitude. And then at 6 kilometers, where you then have some of the Virgo buildings, you will then still be able to see these disturbances, but they have already gotten quite a bit weaker. But for sure, this one here at near 2 hertz is still quite relevant to the Virgo detector, for example. If you look at this amplitude decrease more quantitatively, then you can see that there's a strong decay when you are relatively close, within 3 kilometers to the wind turbine, and then it is going over into a weaker decay. And this is simply because at small distance you have the strongly damped surface waves dominating the disturbance, and then at some point it's taken over by the weaker body waves, which, however, then decay less quickly as a function of distance. Again, this is something really important to understand, these plots. We are using these also to evaluate this kind of problem for next generation detectors. So again, apart from doing great science, the LIGO and Virgo detectors tell us a lot that we have to understand, lessons for the next generation facilities. Okay. Now, the first line of defense against seismic disturbances is the Virgo superattenuator, which is probably really the iconic component of the Virgo detector. It is one of the biggest differences between the LIGO and the Virgo detectors. And the idea in the beginning was that this kind of large suspension system, so this is like inside 10-meter tall towers, this type of large suspension system would make it possible eventually for Virgo to observe gravitational waves at much lower frequencies. On the next slide, I can be more quantitative about what this means, but that was the initial motivation. But we'll also see that it's not all about seismic isolation if you want to go to low frequencies. And for sure, that is another important lesson to learn. Because despite the differences in seismic isolation, you saw already on the O3 sensitivity curves that LIGO and Virgo are not that different. So they have completely different designs, mechanical designs, but the sensitivities at low frequencies, especially in displacement, are very, very similar. So it seems like, you can try hard and do seismic isolation and try, but there are other problems that are not addressed by that. And frankly, these seem to be as hard of problem as seismic isolation. So we have to be careful when getting our hopes high. for the future in some sense, okay? We have to be careful about this. Now, to show a little bit about what the super attenuator is doing, so here in this picture, first of all, you see a little better what the mechanical concept really is. So you have here a series of pendula. So there's one filter stage suspended from another, and you can see essentially here how this is being done. So first of all, of course, suspension here means that you have a regular pendulum in some sense, okay? One that can swing in horizontal direction. But then you can see on these pictures as well that what happens is that you have a frame, and from this frame you have cantilevers going in, flexures, whatever you want to call them, and they meet at a central piece that holds them together. And then from the central piece, you are then suspending with a wire the next stage. Now, this kind of suspension gives you flexibility in the vertical, and so that that super attenuator is not only isolating, of course, then in the against horizontal ground motion, but also against the vertical one. And since it is, and this is another feature, since over a large part of the suspension system, not at the very end anymore, but over a large part of the suspension system, it is a single wire connecting these filters. So that means that you also have softness in rotational degrees of freedom of each filter stage, with respect to all three rotation directions or axes. So, in that sense, clever concept for sure. And I assume that for what it was meant to do, it is actually working perfectly. But as I said, it's not really solving all of the low frequency problems. Now, you can see here, at least by design, what it means to have such a super attenuator compared to, for example, what LIGO is having, advanced LIGO. So here, this is what the seismic isolation function looks like. That means like if you have a certain, if you have a ground motion or here some vibration at this filter zero stage. Now, no, it's actually not filter zero. This is really ground motion. So if you have ground motion, then it translates into a motion of the test mass in the following way. There are certain frequencies where you have resonances where the ground motion is actually enhanced. But then above some frequency, you really see that you achieve attenuation. And we are looking here at this curve here for Virgo. And already, at a few hertz, essentially you are taking out most of the ground motion. So that's good, very effective. At these frequencies, as far as we know, not that anybody was really able to measure it in any way at the Virgo detectors, but if this here is true, then we would be orders of magnitude more effective than the LIGO seismic isolation at these frequencies. So this again telling you that this design was chosen for low frequency gravitational wave observations. Fine. So that is the seismic isolation. Now, what it's worth, at the moment, and in the last science run, as I said, okay, Virgo didn't really beat LIGO at low frequencies, and it might not. We're not really expecting it to beat LIGO in sensitivity in any of the two, or in the next, at least in the next observing run. But what it also means, what it at least means, is that when it comes to seismic isolation, you can have let's have a slightly more optimistic planning towards the low frequencies. And for that matter, I assume the managers of the project decided to look into Newtonian noise cancellation as one of the technologies that should be developed for Virgo to improve its low frequency, as one of the tools to improve low frequency sensitivity. Okay, so let's then get to Newtonian noise. So here's what it generally means. Newtonian noise is simply noise produced in the detector because the suspended optics especially the task masses, or the four task masses of the Virgo detector couple gravitationally to the environment. Now, because in the environment there are things happening that change the density distribution. And we're not talking about macroscopic effects like some object moving. I mean, even that could perturb gravity in a significant way. But we are really talking about environmental fields, acoustic fields, seismic fields, temperature fields, things that are always present that you cannot avoid in the vicinity of your detector. And then you have to model essentially the coupling and predict the noise it produces. Now, already in the very early phase of the planning of the LIGO detector, Ray Weiss knew that, for example, I'm picking his name because he did the first analysis. He understood very well that this gravitational coupling exists, and so people, if you want, maybe the sum of the so in some sense the predictions people had about how strong this effect is and what type of noise it would produce in the detector influenced the overall design of the detector, in the sense that you always try to avoid this kind of noise in your detector, because gravitational noise is something that you cannot shield. You cannot shield your test masses from Newtonian noise. And so once it appears, it poses a sensitivity limitation. And at the time of, in the early days at least, people didn't really think that there would be a way to reduce that noise in the detector. Today, we will see, we have ideas about what to do, but at that time it was kind of seen as part of an infrastructural noise, something that is giving us something like an ultimate sensitivity limitation at low frequencies that you cannot work on with some set of technologies, let's say. Okay, so these predictions, these analytical predictions, I will show now in the following how to obtain them, at least in the example of the seismic field. This is how these fluctuations look like, the spectra. And this is a combination, this plot here, of three models that I'm showing at this part here. And this part here is a real observation of gravity fluctuations. So what do we see here? This is like 0.1 millihertz to 10 hertz. So this is a large band. And here we see the gravitational noise in terms of acceleration noise. And the observation here at very low frequencies is obtained from superconducting gravimeters. So when they make, when you take a superconducting gravimeter and you look at the data, then you will see here a spectrum which is produced by the atmosphere. So atmospheric pressure fluctuations produce that kind of noise in superconducting gravimeters. And these are used to make measurements for seismology, geophysics, atmospheric science as well. Now, if you wanted to, and they actually have this in place, you can deploy a pressure sensor next to your superconducting gravimeter, and then you can use the data from the pressure sensor to clean up your gravimeter data. And this is happening. People, geophysicists are doing this. So they already do what we want to do now in Virgo in the future. They've already been doing this for years, and we call this Newtonian noise cancellation. Now here, these spectra are, this purple one here is an acoustic spectrum of acoustically or gravitational noise produced by the acoustic field of the seismic field, but at the surface, and of the seismic field, but underground. Now, so that means first of all, what you can see is from, if you look at the underground spectrum, that means something that you would see a few hundred meters underground. Then you see that there's a reduction of the gravitational noise. And this is simply because the seismic field is much quieter underground than it is at the surface. So it helps to go underground at these frequencies, not so much at low frequencies, because what happens here is that the relevant, the question is, how deep do you have to go to avoid these fluctuations? And that answer, so you have a length scale, which is the depth. So what is the second length scale of your problem to compare with? What does, and the answer is the seismic wavelength. So how long seismic waves are essentially tells you how deep you have to go to avoid the gravity fluctuations produced by these seismic surface waves. And so here we are having seismic waves which are like 10 kilometers long or even longer. And so you would have to go underground 10, 20 kilometers to see a very, very strong reduction of these gravity fluctuations. So there's really no way to escape them with a gravitational wave detector. This, however, is an advantage that we are playing with, for example, when it comes to Einstein telescope, as I will show you tomorrow. But what you can also see is below 0.1 hertz, it is not the seismic field anymore that is producing the main gravity perturbation, but it is the atmosphere, consistent also with what the measurements are with the superconducting gravimeters. Okay, now the way to model it is that you start with describing the density perturbations in a linearized way, so as a divergence over a displacement field. And here is the unperturbed density of the ground. And this, in some sense, works. I mean, this is a divergence, but it even works to calculate surface effects. So it is it is all you need. This is of course this is a consequence of the continuity equation, and then inserting this into an equation to calculate gravity perturbations, you obtain you can split this up into two expressions: the surface terms and the bulk terms, which depend on an integral over the volume, and here over a surface of, for example, the surface that we are talking about here can be the surface of the Earth, and this would be the internal volume of the Earth. And so inside the ground, you see what matters is the divergence of the displacement field. This is the compression and decompression that is produced by the seismic field, which leads to gravity fluctuations. At the surface, it is the displacement in normal direction to the surface. And so these two can be added up to get the full gravity perturbation. These specific equations are valid only for a uniform medium, but in any case, this is how the math looks like. Now, if you take these equations and you insert for the displacement fields here plain seismic waves, and we heard that there are Rayleigh waves, compressional waves, and shear waves. Now, if you take the expressions for these three types of waves and you insert them into these equations, and then, for example, you have to solve the integral then, but that's not so hard. Then also what you can do in addition to that is you can average over propagation directions, because let's say you are not interested in the effect of a single seismic wave, but you know that on average the seismic waves come from all directions because it's a random field. And you can assume, for simplicity, that the distribution is isotropic in propagation directions, or the source distribution. So then you can average over the propagation directions. Then you obtain equations like these here. So this is for body wave Newtonian noise. And this is the power spectral density, or the spectrum, if you want, of acceleration, again, of test mass acceleration produced gravitationally. And there's this factor on top with the Newton's constant G, and the density again, here again, assuming that we have a homogeneous medium characterized by a single density parameter. And now here you have now a split into compressional waves So this is the displacement of the total displacement produced by compressional waves, and this is the total displacement produced by shear waves. And this entire equation here holds for a detector which are located underground. So the test mass is underground; it's not at the surface. So essentially, it assumes that you have the medium all around the test mass in all directions. And then you get this kind of expression. You can compare this with what you get from a Rayleigh wave. So as I said, this is a surface wave whose propagation is confined in 2 dimensions across the surface. And in this case, there's a new parameter that really matters a lot, which is the distance between the test mass and the surface. Now, that might not, seem so relevant maybe at first sight, because if you think about LIGO and Virgo, you might think, okay, we know that the arm is kind of going along the surface, so the distance between the test mass and the surface is maybe 1.5 meters or something like that. Does that kind of distance really matter for Newtonian noise? It turns out it does actually for Virgo quite a lot, interestingly, and we didn't really expect this before, but I will explain you why it really matters so much. But above all, it matters for a detector that is underground, because now you can be hundreds of meters away from the surface, and then this exponential expression here matters a lot, and it can make this surface Newtonian noise completely insignificant in underground detectors, for example. Okay, now that is analytical modeling, and for 20 years, that's all that happened. Now, more recently, we started to look into numerical models because we have to describe Newtonian noise in more and more complicated environments, because we enter into the details now, which really matter at some point. And then you really have to come up with a generic description of that, which holds without any assumptions and simplifications, and that is the dipole equation. So here you have again the displacement field inside this integral. And here you have now the density, but the density as a function of position. So you can even calculate Newtonian noise now for an inhomogeneous medium. Of course, in reality, the problem is that you do not know the density as a function of location underground. You can make guesses, but you do not really know it perfectly. The same is, by the way, also true for the displacement field. You can model it, yeah, but in reality, what do you know about it? I mean, you can measure it at the surface, but even then, you don't know it everywhere. You have to choose locations where you measure the displacement, but then it just gives you it still gives you an incomplete picture. For sure, at the Virgo side, we have no understanding of displacement underground. So we have, you have this equation, great, but in practice, it comes with, challenges to use it. Now, for numerical simulations, nevertheless, it is really what we are using all the time. So we are simulating. What we are doing is we're setting up models for this medium, finite element models. Then we can simulate the displacement field in such a medium. And then with that kind of simulation, you can carry out this integral, and you can calculate the gravity fluctuation at the test mass and the noise that it produces then in the detector. Okay. We have done this for the Virgo detector, and here the challenge was the following, and this is something that we realized a bit too late, that the relevance of that. So a long time ago, we had the idea already that, okay, since there is this parameter, the distance between the test mass and the ground, and since that one really matters for the Newtonian noise produced by Rayleigh waves, we thought like, okay, is there a way for us to increase the distance somehow? And at the time when we thought of this first, we thought about, okay, for the LIGO detectors, can we change the site in some way so that the distance between the test mass and the ground is increased? And so the idea was to dig recesses around the test mass to take away the ground around the test masses, and that would reduce substantially your Newtonian noise. Now that seemed kind of crazy to LIGO people because digging, we're talking about recesses which are like several meters deep and maybe 10 meter wide. So these are big structures, and it seemed kind of crazy to do that after the detector is constructed. And so that idea was kind of forgotten. But then we realized at some point that Virgo has this already. Of course, they didn't make these structures because of Newtonian noise reduction. They had this for another reason, because if you want to install the test masses, then what you do is essentially you are having a platform here that you can lower, and then you can work on the payload, let's say, and then you can bring it back from below into the tower here. And the access of people is through an opening here. So these are clean room for test mass, which you use when you want to work on the payload here. Okay, so you have this in Virgo under each of the test masses. And these are big. These are 3.5 meters tall, and they are 14 meters long, and several meters wide, especially in the central part. These are huge structures. So at some point we thought, okay, well, maybe we are lucky. And we created finite element models where this kind of geometry is implemented, and we propagated seismic waves through that finite element model, and we looked at what is the reduction that you achieve in Newtonian noise, and it turns out you get a lot. So here are several curves showing you the reduction in Newtonian noise. So one is the level that you would have without any recesses, without any of these buildings, clean rooms under the test masses. Now, if you instead consider these clean rooms, and now if you assume, that was our first step that we did because we didn't know at that time how fast the seismic waves are. If you assume the seismic waves to have a speed of 250 meters per second, then you already get to a Newtonian noise reduction shown here, which is a factor 2 at 15 hertz. And a factor 2 at 15 hertz, I mean, it doesn't sound like much, but if this is for free, we got this for free. We didn't do any work. We just did these analyses, and we found, we probably have a factor 2 reduction. That's great. So that is was a huge advantage, of course, at this point, or lucky day for Virgo. Now, there was a second lucky day, however, because at some point when we deployed arrays at the site to understand the seismic field more carefully, we measured also the speed of seismic waves. And what we found is that the seismic waves are much slower than 250 meters per second. They are 80 meters per second, or, consistently below 100 meters per second. And we're talking about the Rayleigh waves. And now this is because of the soil that is at the surface, which is a very, very slow material, soft, slow material. Now, from the discussion that we already had about this, when you look back at this term here, what this means is e to the minus 2 pi, and that's the distance parameter between test mass and surface, divided by the length lambda of seismic waves. Now, the shorter the seismic waves, the stronger is the exponential suppression. That means the slower the seismic waves, the better for you. And that is really what you see here as well. If you now take into account the dispersion, then in the end, overall, you get a Newtonian noise reduction, which is shown here in red, which is over the entire Newtonian noise band. And if I talk about Newtonian noise band, I mean like 10 to 20 hertz. We have a factor 3 reduction. And now if you split this up, because it's a little bit different for central building and end building, because in the end what we find is what matters mostly is the minimal distance between a test mass and the leading or trailing edge of this kind of structure. And here we have only a few meters, while here we have 6 meters at the end stations here. So this is the reason why we have a stronger Newtonian noise reduction for the end test masses than for the inner test masses of Virgo. And this is what you see here as well. For the inner test masses, we have like a factor 2.5 reduction, and for the end test masses, 5 to 10. Now that's huge, but that also tells you, how effective these kinds of structures can be. But of course, that is only so because the waves are so insanely small, short or slow at the Virgo side. Now, what this actually means is that, and this happened all later because the way this was like, okay, where we had some Newtonian noise estimates initially, we thought like, okay, we need a new Newtonian noise cancellation system. Now let's set all of the arrays to study the seismic fields better. Then we found these kinds of results because people came in to do these studies carefully. And what the consequence of this is that we don't need Newtonian noise cancellation system. So great news. What it means is, and we don't need it means we do not need it in the next science run. We probably won't need it in the one that follows. Maybe we will need it then in what we call post 05 scenarios. So possible usage of the detector infrastructure after the 05 science run. So, but anyway, this is really kind of eliminating the need for any Newtonian noise cancellation system. You can see this here in the predicted Newtonian noise spectra. So this is here our most ambitious sensitivity target for 05. And you can see that with all of these suppressions now, the Newtonian noise from seismic fields falls largely under that kind of noise level, except for some peaks because of, that are also in the seismic spectrum. So, and that is, of course, good news for Virgo. Now, all of this is really very strongly model dependent in some sense, because we are neglecting many properties of the seismic field at the site. What we are using in reality for these predictions, the only thing that we are using, or there are two quantities that we are using, the dispersion or the speed of the waves and the spectrum measured at some point, inside the buildings of the Virgo detector, nothing else. But what we actually know is, if you want to get really into the details, what another really important parameter for Newtonian noise is the correlation between 2 points of the seismic field. Now that is really in some sense, the key parameter, and it even substitutes the need, or it eliminates essentially the speed as a parameter from your models, the speed of seismic waves. You are instead expressing the relevant aspect of the field in terms of seismic correlations, and this is how a Newtonian noise model looks like. That depends on seismic correlations, where rho here is, let's say, the distance between 2 points. In this model, this is a homogeneous model, so it's only the distance between 2 points on the surface that matters in a homogeneous model. While in general, it depends on the 2 absolute coordinates of the points that you correlate. So in reality, you need 4 quantities on the surface to as variables for this correlation. But for a homogeneous field, it's just this one parameter, which is the distance between 2 points. And now there's a kernel here that you multiply to this, and then out of that you can get again an estimate of the Newtonian noise spectrum. And the good thing is that if you do that, then you at least include all the relevant observable properties of the seismic field in your model. Okay. And we did this as well. We did correlation studies. Now I will here give also an example of LIGO, because LIGO is so much less complicated here. So what is why is LIGO less complicated than Virgo? So the main thing is that LIGO has around the task masses a perfectly flat surface. So a seismic wave is propagating through along the surface without really being perturbed. While at the Virgo side, we have this clean room. And so when a seismic wave comes in, it is partially reflected from this structure. And it makes the whole field strongly inhomogeneous. So the homogeneity is also visible at the LIGO side in the correlation measurement. So what you can see here is the following. Take a pair of seismometers. So you deploy an array, and we had like 38 sensors at the Hanford detector. So take these 38 sensors, take a pair, and now measure the correlation at a specific frequency. This is now for 15 hertz. So at a specific frequency, you measure the correlation between two seismometers. And now you take the relative position and you mark it here in this coordinate system. And then the color of that marker is your correlation. So, do this for all pairs you have. Of course, there are hundreds of pairs that you can make out of 38 sensors, and make these hundreds of points. And look at the correlation values. You can see here, if the separation is 0, this is like the correlation of a seismometer with itself, then the correlation value is maximal, equal to 1. Now, if the distance, the separation changes, then the color drops a bit. And you can see here that it is falling. Now, if this is really all Rayleigh waves, that determine this, the seismic correlations, then what you would expect for an isotropic field is a Bessel function that describes the correlation here. And so here it gets negative, but then you can also see after it here it starts to rise again. Here it is 0 and here it is positive again. So it is like kind of an oscillating pattern that you have here. And it looks very regular, right? So the fact that you have no points here, which are very strong outliers, because these all come from pairs that are, that can be very distant to each other. They can be monitoring completely different parts of around the test masses, but still they are measuring correlations that are similar, consistent with the distance between the two seismometers. So this is the fact that you have a very uniform plot here means that you have a very homogeneous seismic field. Now, this plot here at the Virgo side would look like noise. It would look like almost completely random. And this is why we are not plotting it like this in this way. We are making you cannot see this probably very well from where you are, but the way we are plotting this, and let me just explain at least the plot method, is that for each location of a sensor in this building here, we plot again the correlations with all other sensors in a small inset of the array configuration. So you can see here each cluster here is one sensor location, and on each sensor location we are kind of representing the full array configuration again to be able to see what is the correlation with each of these sensors around here. And in this way, you can also kind of analyze the inhomogeneities in the field. And this is the analysis that we had to do. And then we use that in a fully generic equation for inhomogeneous seismic field to come up with Newtonian noise estimates. And model, for example, the gravitational coupling between certain vibrations on the surface and the test mass. And what you can see here, and I will come back to this later because it was important for the design of the system in the end, but what you can see here for the end test mass, which is located here, is that here, first of all, the coupling is weak inside this area because this is where the distance between the test mass and the ground is larger, okay? This is the action of the clean room under the test mass. Now, at the edges, we have the most important points when it comes to gravitational coupling. And so here you can see it's maybe a bit surprising that this edge is more important than this edge because that one is closer. This is 6 meters and this is 8 meters here. This one here is more important because it turns out that on this side, you have all the machines that produce the noise at the Virgo side. So this is a machine room. And all of the waves, most, not all, but most of the waves come from here and they propagate through the building. And so the amplitude here is much larger than on this side of the building, the amplitude of seismic vibrations. And so this is why the gravitational coupling here is stronger, because it's just the amplitude of the motion is stronger here. Okay. Now, to complete a little bit, I will only say this briefly because we are not using this yet for Virgo, but we have to become even fancier with our modeling in the future, because there's one big question unanswered, which is, well, if you have measurements, but the measurements at the Virgo detector were of course only with surface arrays. We didn't drill boreholes to look what's under the ground, so under the surface. So in the end, if at the point when it becomes important to understand the underground displacement as well, it is clear that you will have a highly incomplete understanding in terms of measurement of the underground seismic field, because it costs a large amount of money to make a borehole, deploy a seismometer, and make a measurement. It is so costly that you can maybe have only a few of these boreholes. And so you will have a highly incomplete measurement always of underground displacement. For now, we do not really care about this at Virgo. In the future, in the post-05, we might actually care about this, but not now. Now, when you have these gaps in your measurement, but you really need to somehow know what the displacement there is, or more specifically, not the displacement, but the correlation between points, because the correlations is what really enters your models in them. So if you want to know this, then of course what you can also do is you can set up very complicated numerical simulations with, where you could use software like COMSOL, ANSYS, and there are also specialized seismic software to do this, where you do essentially an equation solver where you use the linear elastic equations, and you have sources of seismic waves, and you simulate these sources as forces and acting on the ground, and then you really propagate in a dynamical way the seismic waves through that model. So you can do these type of fancy simulations, and you can try to use them to fill the gaps. So you have these simulations, you have the measurements, but now the question is, how do you put these two together? Okay, so we have done this part already now, not as part of Virgo, but as part of ET. So a student of mine did these numerical simulations. And so one thing that you can do with these simulations is directly solve for correlations and power spectral density of random seismic fields produced by a random distribution of seismic sources. And then you can get results for gravitational coupling, or for simple seismic displacement in such a topography here. But then in the end, you have to come up with a way to get it together. And this is what we call Bayesian Newtonian noise estimation, where you have the measurements, where you have the numerical simulation, and you have to get it together. And in reality, it's not only for Newtonian noise estimation, it's actually for something far more important, which I will also discuss for Virgo, which we have done for Virgo already, which is the optimal placement of your sensors to do Newtonian noise cancellation. Okay, and so let me come to Newtonian noise cancellation. This is what we have now at the Virgo detector in preparation of the upcoming science run. We have 30 seismometers around the end test masses each, and 50 here in the central building. At the central building, we found that for good Newtonian noise cancellation, you also need to place some of them in the clean room under the test masses. But 40, the majority, are here at the surface level, and then so 10 are at the basement. And this is how we approached this problem. So what we did is, first of all, well, let me explain this later. Let me finish first what Newtonian noise cancellation means. So the data from all of these sensors is now being acquired. Of course, everything has to be synchronized. And for instrumentalists, we did some interesting, maybe initially quite risky choices about how to do this. For example, the actual seismic sensor is paired with electronics that digitize immediately the data at the sensor, and then it is transferring already digitized data to central data acquisition boxes. And so what we had to do essentially was we had to take the Virgo timing and we had to distribute it to all of the sensors with the power, and then get back the data from the sensors. And this is all done through the same digital channels. And then all of these data go to one server where we are inserting it into the Virgo frames. And so we have 110 seismic channels there. So these sensors are only measuring vertical ground vibrations. And I don't have time today to explain why only the vertical, but in any case, you could imagine this to be connected to the point that the gravity perturbation is produced by normal surface displacement. We saw this in the equation, in the analytical equation before. And so we are only interested in the normal, monitoring the normal displacement. In reality, the story is actually a bit more complicated because you could profit from the horizontal, monitoring the horizontal displacement as well. But in any case, so at Virgo, we have the vertical ground motion monitored. So data from 110 sensors. And now we already have the pipeline that is doing the cancellation. We are now just, as I speak, these days we are translating this into an online pipeline, something that automatically runs on the data when it comes in and immediately produces a clean gravitational wave data channel. At the moment, of course, there is no gravitational wave data that we can test on, but we tested on for example, some seismic channel. So we are trying to subtract, let's say, noise from some seismic channel. Now, this all goes then. So what this is doing is like, I'm calling this magic linear box. On the next slide, I will tell a bit more about this magic linear box, but it's essentially an optimal linear filter that takes all of these data, processes them into an output that is then subtracted from the noisy gravitational wave data to produce your clean gravitational wave data. And this part here is not new. So also at LIGO, they've already done what, in post-processing, what you would call feed-forward noise cancellation. Not for Newtonian noise, but for other noises. And in some sense, in other forms, this is also part of the standard control scheme of certain parts of the interferometer. So I think the technique is not so new, but what is new is the fact that you are using more than 100 channels simultaneously, which all have partially correlated data. And so the filter here has really millions of coefficients, which is a new scale of the problem. So this is how the simplest implementation of that filter looks like. We call it Wiener filter. And it is calculated in the following way, or it's determined by the following equation. You have here a vector of filter coefficients. And let me start with this equation here for you to understand what these coefficients are. So essentially, you have the seismometer data from a certain number of seismometers. And you multiply the samples of the time series with coefficients of your filter, and then you're summing all over it, and the sum of all of this is the sample in your output. And this sample is what you subtract from your gravitational wave data, sample by sample. So you get one sample of gravitational wave data, you subtract one sample, which is the output of your filter, and then you're doing the sample by sample. But for each sample that you're producing here in the output of this filter, you're using not only the present sample of the seismometers, but also past samples. So this is what this here, the index here means. You're going from sample n back, which is a time index here, if you want, n. You're going back into the past by capital N samples. And this is what we call the order of the finite impulse response filter, FIR filter. So that's the filter order. It really tells you on how far in time you're going back, how many samples you're going back. And all of this. Now the question is, how do you calculate these filter coefficients? You want to use the best one. So that provides you the best estimate of the noise you're after, which you are then subtracting from the data. And this you can calculate as a Wiener filter by setting up a big seismometer correlation matrix. So this is the matrix that has all the correlation between all the seismometers. But now this would only be 100 by 100 seismometers. So this is 10,000 correlation coefficients. Now that's not so much. I talked about millions. Where do the millions come from? The millions come from, again, because we are not only correlating different channels, but also between different times, because we have to go back in time with this filter. So I told you we are going back in time by a certain number of samples. Because of that, we also have to correlate different times between the different channels, and that in the end results in millions to tens of millions, maybe even 100 million coefficients in that matrix. Okay, then we have a Wiener filter, and then here this is the correlation similarly, but between all the seismometers and your gravitational wave data. Okay, that is clear. You need this kind of object here, because how else should you be able to understand with your filter what is the coupling between your seismic field and the data that you have in the gravitational noise that you have in the data. So that information doesn't come out directly of a seismometer correlation matrix. You need a correlation matrix, a correlation vector as well, if you want, between seismometers and gravitational wave data. Now, this filter here, this vector of filter coefficients, you could get now by inverting that matrix and then multiplying it to this equation. So that on this side you have the Wiener filter coefficients, and here you have then an object that gives you the coefficients. Now, this is fine. This is how, in principle, it works with Wiener filtering. But the problem is that you do not know these correlations perfectly. You just estimate them. So you're taking a stretch of data, of seismometer data, and you are using that data to estimate the correlations. And in these estimates of the correlations, there are statistical errors, because only if you have infinite amount of time to estimate your correlations, your estimates will be perfect. So if you have a finite stretch of data to estimate your correlations, then you have statistical errors. And if you have millions of coefficients, and if you then do an inversion of that matrix, which we already know, some of these seismometers are very close to each other, so they will have highly degenerate data. That is all very bad for you when you do matrix inversion. So you have statistical errors, you have near degeneracy, and now you're inverting this thing. You can be sure that the result of that has a big impact from the statistical errors. So the Wiener filter coefficients that you have here have substantial errors in this specific scenario, because you have millions of coefficients. This is the problem of time domain Wiener filtering. It turns out that if you did it in frequency domain, the dimensionality of the problem would be strongly reduced, and then the statistical errors go down, and you perform typically much better in frequency domain than in time domain. But we have to do it in time domain because we do it as an online process. And there are other reasons why we do it in time domain. Okay, now you could say, okay, but we could take longer and longer stretches of data. I mean, why not take a month of data? And in fact, for some analysis we have done in LIGO and Virgo, we do take a month of data, and we do estimate the correlations very, very, very precisely. And then we could calculate a very, very precise Wiener filter out of this. But here's the problem. Nature is working against you. Unfortunately, it is limiting the stretch of data that you can use, because the field, in reality, the seismic field, is not stationary. It changes its properties over time. So the Wiener filter that you calculate, which is based on these correlations, the correlations between the seismic correlations and correlations between seismometers and gravitational wave data change with time, slowly. Not like every second, but there are slow drifts. For example, in the weekend, it can be different than during the week, during the working days, or at night, it can be different than during the day. So there's this kind of slow change in correlations. And so what you want is to evaluate these correlations or update them regularly. And that sets a limit to how long of a stretch of data you can use. And now you see the full, the full circle of the problem. You would like to get good estimates of your Wiener filter, but you cannot because the field is not stationary. You have to go through an update process. And because of that, the Wiener filter is limited in its performance. It is not working as perfectly as you think. So there might be ways to actually get something even better than a Wiener filter. And so we are doing studies for something better. And so the one thing is you could calculate the FIR filter not by using these equations here based on correlations, but by doing a gradient descent. So essentially, think of these, as some coefficients. You could even calculate them initially as a Wiener filter, but then you are adding to this a gradient descent to optimize further, because the dependence on statistical errors you can remove by doing a gradient descent to further optimize these Wiener filter coefficients. And this is something that we have done, and I'm showing on the next slide, what the result might look like. There's something we call Kalman filtering, which is essentially an automatic tracking of changes in correlations. So the Kalman filter, it depends on who talks to you, but one way to think of the Kalman filter is being a Wiener filter, but in a way that it recursively updates the correlation estimates for you, so that you always have automatically the best estimates of the correlations used. But in the end, also here you are subject to some extent to statistical errors. But it should work better in principle than a Wiener filter. And then you have also machine learning that you can use as a noise cancellation filter. Now, that is interesting. Then the results that, just to give you one example to tell you that you can beat a Wiener filter, this is just simulation. But no, it's actually, it's partially simulation, but it is also using seismic data. But what we're doing here is essentially, or what I did is I took array data and I calculated a Wiener filter to subtract the seismic signal in one of the seismometers. And I did this with a Wiener filter, and so I get a residual noise spectrum, which is the orange one here. And then I did a further optimization using gradient descent on the Wiener filter coefficients, and I got something better. And this is just explained by the issue with the large dimensionality and the statistical errors that you have in the Wiener filter estimate. So it can be done, and we expect similar effects to be relevant when you use Kalman filtering or machine learning. Now, last slide. No, not last slide. Second last slide. But what I want to show is an important aspect of how we got to the design of the Newtonian noise cancellation system at Virgo. So what we first did is site characterization. So we deployed inside the building an array of seismometers just to understand the seismic field. So that's where we measured the dispersion. That's where we started to understand where the sources are, what the sources are of the seismic waves. And so we studied the correlations between the sensors and so on and so forth. Very important. Then what we get out of this is essentially we can construct a surrogate model of the seismic field. So we are taking the correlations, but we are taking these as anchor points for a continuous representation of the seismic correlations between any 2 points on the surface. So that is what we call a surrogate model. So that one is able to calculate for you the correlation between any 2 points in this homogeneous field. And now when you have this, you can use this surrogate model also in your equations where you connect the seismic correlations to an estimate of the gravity perturbation. And now doing all of that, you can, so in some sense, you can use a surrogate model here in this equation for that expression here and for these two correlation matrices. So you can calculate a Wiener filter, and you can, based on that, now calculate the optimal seismometer placement on the surface to achieve the best possible with a certain number that you have of seismometers, what is the best Newtonian noise cancellation that you can do depending on the location of these sensors. And that is an optimization that we have done for Virgo based on these initial measurements. And in the end, we came out in this optimization process. First of all, what you see is that as a number of seismometers that you have, you get a certain Newtonian noise cancellation. So this means here, if you get here to a value of 1, then you would be able to cancel all of this Newtonian noise. But in any case, this here comes with an optimal configuration, which is given here by what you can see here now for 30 sensors. So this is our optimal array configuration that in the end is what we did, how we deployed it at the site, at the end stations at least. And now last but not least, we are going now even a step ahead and we are doing robot arrays. So here's the thing, our actual understanding of the field is still limited because we measure only a finite number of points. Now what you can think of is put the seismic sensors on a mobile platform and move it through the building. And so you have now an array of, let's say, 20 of these robots which move through the building. They make a measure, they stand still at some point. They make a measurement, and then you learn something new about the seismic field. You re-optimize the array configuration, and you move then the robots accordingly. Now they make a new measurement. They learn something actually new about the seismic field, and you can re-optimize. And so you can gradually converge to the true optimum of the array configuration. And what we have to do here is sort out a lot of practical issues about transferring data between these mobile units and the frame builder in Virgo to use a wireless protocol that is not disturbing other wireless data communication transfer and so on and so forth. But in any case, this is something that is being done right now under the great an effort by the Ego robot team. And this is very exciting. So this is then the next step of what we can do with Newtonian noise cancellation. And that's where I want to stop. Thanks.
Okay. Are there questions? If not, thank you very much, Jan.
Thank you, everybody.